Out of all the things we looked at this morning, this one I guess will get recorded, but this is the most relevant because we were talking about fluid dynamics, I guess, for the first time. And last time we introduced linear flow through Bernoulli along a streamline, bless you. And we said there were two kinds of flow that we could look at. We could look at flow or look at the behavior along a streamline, which was fine. Or we could look at flow perpendicular to that streamline and what the pressure distribution would be. And so this is the closest analog to this. It's not a fluid analog, but it's actually reasonably close to the reality of what we look at. And that is what we'd like to know is that if you push fluid around a curved surface, what is the effects of the fluid pressures as you go normal to that fluid pressure, fluid surface? In other words, away from perpendicular to the aerofoil or the wing, how does the pressure change? And so that's kind of what we'll look at today. So I guess I didn't record the previous ones, but that's fine. Before we get going, any questions from what we talked about last time about midterm, which is on coming Wednesday? No? Okay. All right, so I guess you've just got through your first Thirsty Thursday. I had a Thirsty Thursday as well last night, actually, I'll have you know, so it's fine. So you're not the only ones who get to do it as well. So what we talked about last time, I guess we're slightly off the screen, but we moved, as you know, we moved from talking about statics, from fluids within a container with no circulation, to fluids that circulate. Last time we talked about the idea that we would have for instance, an airfoil of some form, and that airfoil would have circulation past it. And that circulation would allow us to write behaviors at potentially two different locations. An upstream location, which is how we might like to codify our behavior. It doesn't matter now, we could write it upstream or downstream, but when we talk about energy losses, it'll be important that we write from upstream to downstream in the equation. And if we do that, then we can write Bernoulli's equation, which we talked about last time, which is this expression here. We can write it in a differential form. Typically, we'll use it in its regular form, if you like, which is if we divide this, for instance, through by g for every component, we get pressure over unit weight plus v squared over 2g plus elevation only is constant. And so what we found out last time, and what we did last time, was we wrote it at two locations 1 and 2. We have 6 unknowns, and so long as we know 5 of them, we can solve for the final one. And so we did the example with a jet engine, for instance, putting pressure on a truck to represent this United Airlines thing that we had going on last time. So we wrote it upstream and downstream to be able to do that, and noted the fact that the things that always confuse people, I think, are that why is the fluid pressure here atmospheric or zero? And that is because when it comes out of this jet engine, if you imagine atmospheric pressure is acting on that jet as it comes out, so you can take it a foot or 2 feet away from the engine, clearly it has to have atmospheric pressure acting on the jet, and therefore, since we know that the fluid pressures are the same in all directions, if it's atmospheric in this direction, it has to be atmospheric in every direction. And so we can define the pressure at this point as atmospheric. We know the velocity. We know the velocity here is 0 because it hits this truck, and we can calculate the pressure. And we did that last time. And so actually it's not very different from the case, if you're here earlier when we were playing the videos, of the jet pack of a fluid going down here, striking this to velocity 2 is equal to 0, and we have it coming out of here at velocity 1. And we could do the same thing to calculate the force which is applied to keep the rider buoyant above the water. And so we can do that calculation. So Bernoulli allows us to be able to do that. And so the other thing, I guess, with Bernoulli is that certainly from all the things that we've talked about in terms of manometer equations, if you think about looking at 2 points within a container, if you identify points 1 and points 2, you can imagine them joined by a streamline. Then if it's a static container with stagnant fluid, by definition this term will be 0, and you just have these 2 remaining terms left. And so if you write the fluid pressures between 2 points, you'd have P1 over unit weight plus Z1 is equal to P2 over unit weight of the fluid plus Z2. And if you work this out, I guess if you just multiply both sides by unit weight, then you'd have an expression that says that if you rearrange it, P2 is equal to P1 plus unit weight. What's it going to be? P2 is going to be Z1 minus Z2. And so this is just the manometer equation that we have. And so Bernoulli is just a manifestation of that. If you throw away the velocity term because it's not circulating, if these 2 points are not moving at any velocity, then you end up with a manometer equation. And so that makes perfect sense as well, because we derived it from the manometer equation, which is dP dz is equal to minus unit weight, which is just this, at least for a liquid, this distribution that if you have minus z, that this is the distribution of pressure. So this gradient of this line, I guess, is equal to, this is pressure, so this is unit weight, and this is 1. Right? So we know that. So what we've done so far, at least with the streamline Bernoulli equation, which is this one here, is that we have just derived it from this expression with some extra terms. For the velocity term, we end up with this. This is the simplified way that we use it, and we hope that we can write it between 2 points, and we know at least 5 of the variables, and we can solve for the final one. So that's the first part that we've done. So our reason for showing the jaguar going around the circuit in this is that the other way to think about this is that there's also, in addition to being able to look at the flow, the pressures from 1 to 2, you can imagine that we could also be interested in looking at the pressures as we go normal to this boundary. And so one question we might have is if we have a second streamline that kind of parallels this, and we'd have one below as well that would do this, what would be the pressure difference as we went from point number 3 to point number 4 on here? Is that on the screen, by the way? Only just, right? And so the normal Bernoulli equation we just talked about is along the streamline. These are always streamline velocities, Vs, in this direction, and they would be at these points as well. But for instance, you could ask yourself, what is the pressure distribution as you move away from the airport? And so that's maybe just an esoteric question, but it'll be relevant if you're looking at, for instance, the lift that you get from an airfoil. And so that's the question that we'll address today. And so what we'll talk about today is how to be able to get this expression here, which is the equivalent of this expression for the a long streamline behavior. And you'll see that it has three terms. It has an elevation term, it has a pressure term, just like this has a pressure and an elevation term. And it also has a bit more of a complicated term that involves this v squared parameter. And the v squared parameter, at least in this term, relates to the fact that if you're going at some velocity at this point here, and you're going at a different velocity at this point here, then clearly you've accelerated. So from f equals ma, the acceleration, the ma means that if you accelerate something from some small velocity to some big velocity, it takes a force to be able to do that. And if you have a force that does that, then it requires energy in the system to be able to do that. So it has to take that energy from one of the two other components. It's either potential energy, which is present in this term, or pressure energy, strain energy that's present in this term. And so as we talked last time, when we talk about Bernoulli, we have an energy grade line, which represents the sum of these three components: elevation, pressure, and velocity squared term. And as you go downstream, maybe those components partition differently. And that's the same if you look at behavior perpendicular to a streamline. So that's what we're going to attempt to do today. And so that relates directly to the jaguar going around the loop. And so to start with, what you might think is what happens if you're holding a cup of coffee in the jaguar as you go down in through that. So it's the same as if you're in an elevator. If you go around this bend, you'd feel the centripetal force. And so you'd be pushed into your seat by the fact that you're going around this circuit. And so in the same way that you're pushed into your seat, if you're sitting in a seat on an elevator, then an elevator going up, you'll feel heavier than you would do normally. An elevator that's accelerating downwards, it'll be the opposite. And so you'll see those behaviors. So I guess the short answer to this is that if you go through a dip in the road in a car, you get pushed into your seat, and you can imagine that the pressure distribution in the beaker that you have, instead of just being linear and varying with the unit weight as it does here, you could imagine that it would actually feel as if it was heavier. If you go over a hill and you're pulled out of your seat as you go over the hill, then the water that you have in your beaker, you could imagine just intuitively that it would be, the pressure would be less. The limit would be as if you go over the hill that you get airborne, then you actually would be, I suppose, this, right? It'd be weightless, because you're weightless in your seat as you go airborne, kind of. And so that's what we're going to attempt to do today. So we'd like to talk about not along the streamline, but we'll talk about being normal to the streamline. Okay? We made the case that if we had a weight of some kind that was spinning around, that we could pull it in, and the force that we'd have to apply to this would be equal to the mass times v squared over r, v squared theta over r, where this is the radius. And so we have this little analog behavior. And so we derived some expressions from that, and the geometry that we used, which I'll return to, was that we had a velocity, which is v theta. We have a radius, a radial direction in this direction relative to some kind of fulcrum, which it's rotating around. This angle here is 90 degrees. It's going around an arc. It's not a very good arc, but let me draw an arc. And this arc looks like this. And if you look at the velocity, there's a streamline velocity which is equal to this velocity theta. We're always interested in Bernoulli's theory of the velocity only on the streamline. The streamline is the maximum velocity. If you go normal to that streamline, the velocity is zero, right? Because all the flow is on that streamline. It's the law of orthogonals. Orthogonal to the streamline, the velocity is zero. So we're only interested in the streamline itself. We have a radius on this. So the radius here is 0. The radius here is equal to, I guess we'd call it uppercase R. That's what we'll use. Yeah, I guess those are the main components. But the other thing that we should mention is that we can also define a direction normal to this, which we'll call n. And n points in towards the center of rotation, which is the opposite direction from r. They're directly opposed to each other. And so if you look at those locations, we can define a few things. Our rotation rate, which I guess is this, is in radians a second. And we can define 1 revolution per second is equal to 2 pi radians a second. We need to make that conversion. It's useful. So 2 pi, this term here would be our, what we call omega, not W. We define the fact that this velocity in the tangential direction, theta is the tangential direction, which is the same as the streamline direction, which is equal to the radius that we apply, whatever this radius is. I guess this would be the radius here. Times omega. And so we can also get the square of that velocity. Okay. And if you remember, if I don't take that off the screen, we used this term that the change in pressure with radius was equal to minus rho times the radius times the rotational velocity squared equal to 0. And so what we'd like to do is be able to get, what we're trying to do is get this expression here. And so what we could do is we could take this and we could just keep both of them on the same page. We could just multiply both sides by dr. And we could integrate both sides, I guess. And we could divide both sides maybe by rho g. And so the integral of this is just p over rho g minus, I guess we get some terms out of here, right? This r, we could substitute this for, we have omega squared, which is here. So omega squared is the same as being equal to v theta squared over r squared. So So R V theta squared over R squared G. Don't lose the integration. dr is equal to 0. Get rid of some of those terms. I guess we can get rid of 1r and 1r. And then we can write that if we, for instance, define this term here as being equal to this radius where this happens, which is uppercase R, so we can substitute this R here, then we have a term which is pressure over unit weight, because this is just unit weight, minus the integral V streamline. V theta is along the streamline squared dr divided by uppercase R times G is equal to 0. And I guess that's the term. So in this expression, you remember that when, well, perhaps you don't remember, but when we defined this expression, it was just for swinging things around our head. So we didn't care much about the vertical, the gravitational force that was acting on this. And so if we write this out in its true final form, it will look a bit like Bernoulli in that we have to add this other term in. And the one thing that I'll do is I will put into this, well, no, I won't actually. So we'll realize that this term, this has to be equal to constant because we integrated this. So I guess this is 0. Since we integrated it, this actually should be constant, right? Because we integrate it, you could either integrate it between an upper and a lower limit, or you could just integrate it, in which case it becomes a constant that you don't know. So that's that. And so the other thing that we'll do is I want to switch out this value of R just by convention for the magnitude in the opposite direction. So R is the radius pointing outwards. Swinging it around is the direction away from me. But N is what points in towards the fulcrum that I'm swinging around, just by convention. So I can write this as dn. And if we know that dr is equal to dn minus dn, because they're in the opposite direction from each other, then this just becomes a positive. And so this is the kind of final expression that we'll need. So is it off the board actually? But no, it's still. Actually, it's just on the board, right? So this is the final expression that we'll deal with. And you'll see, of course, that it's the same as this expression that we have here on this sheet. So nothing more. So we just derived it. So you'll see that it looks just like Bernoulli's equation. It has 3 terms. We can do the same thing. We can write the behavior at one point and a second point, so we have 6 components, and hopefully we know 5 of them, and we can solve for the other ones. And so what's a little bit different here is that this term v squared over 2g, which it was, is now a v squared term, but it still has the integral in it. So it's a bit more tricky to deal with. And so what we'll do is we'll just do an example to be able to show exactly how we can use that to be able to do what we want to do. And so what we said we wanted to do was that we thought that if we go from point 3 to point 4, we'd like to be able to see, for instance, how the pressure changes between these 2 points. We know that if we're in a static fluid, then the pressure would change along some line. If it was a liquid, for instance, it would just be a linear relationship given by the unit weight of the fluid, which is constant for a liquid, not for a... So don't think of it as an airfoil with air around it. Think of it as a hydrofoil with water around it. And so we'd like to be able to figure out exactly how the pressure varies as we go from point 3 to 4. And from what we said before, just intuitively, if you're in a car going over a bump that you get lifted off, you'd think that you would be at less than 1g. And so you might think that the pressure distribution, instead of being equal to the unit weight of the fluid, is slightly less than that. Just like going up in an elevator, if you're going up at some, remember when we talked about linear accelerations, that the pressure was equal to the height multiplied by gravity plus the acceleration in the z direction, where z is vertically upwards. If you're going upwards in an elevator, z is upwards and a is positive, so the gravity is increased over what we feel usually. And if you're going down in an elevator, the down direction is negative z, and so the acceleration is downwards and it's negative and it's less. And so we could explain this behavior, at least for linear acceleration, up in an elevator or down in an elevator, based on this equation. This is just z, the depth. And so what we might think is that as you go around a curvature, you're seeing the same thing. And so as you go across this, if you're going over a bump, you're getting thrown out of your seat, and you think you'd be less than hydrostatic. And if you're going into a trench or a dip in the road, you'd think you'd be greater than hydrostatic. And so that's exactly what we'll try and show. Well, we didn't have to do this. We avoided all of this and this and this just by our simple, and we don't need to worry about that. So here's the example. So this is basically the geometry that we're interested in looking at. And so it's a flow system where we have 3 streamlines, I suppose. One is here, one is here, and one is here. And we could ask ourselves, what is the pressure distribution as we go between 2 different streamlines? This is the expression that we'll use. And again, we have 3 components for one point, 3 components for another point. We can equate them to each other. But now, instead of going along a streamline between point number 1 and point number 3, which we did before, we're going orthogonal to a streamline, which is this. So we're going from point 1 to point 2. And so if we apply this expression here, what we could write, I always prefer to write it divided through by unit weight, just because I think it's easier. So this is rho g. And so if we write it between these 2 points, we could write it as P1 over unit weight plus Z1 plus this integral term rho v squared over uppercase R. And n just takes the place of the radius, is equal to the pressure at point 2 plus the elevation plus the integral of v squared over R dn. I guess this is 1 over gravity as well, right? Not so important for this one, I suppose. So if we wanted to evaluate this, the pressure at point 2 is going to be atmospheric, just because it's on the free surface. So I suppose what we might like to do is figure out exactly what the pressure at point 1 is. And so if we look at these expressions here, the radius of curvature of this particular flow here, so the flow is in this direction here. I guess I should use a color other than black. So the flow is along this streamline here. So the radius of curvature here is basically infinity down here, right? So r in this particular case is equal to infinity because it's a straight line. So the radius of a straight line is infinity. This term here, therefore, is infinity. This term here is therefore infinity, and these terms both drop out. And if these terms both drop out, we have that P1 is equal to P2, I'll keep it divided through by unit weight, plus minus 1. If we multiply through by unit weights, you'll recognize this equation straight away, right? It's just that P1 is equal to P2 plus Z2 minus Z1 times unit weight. We always take Z as positive upwards. And so this is larger than this. So this will be positive. And so the pressure at this point here, if I use some useful colors to do this, it'll look just like this. It's getting a bit crowded, of course, but the pressure distribution is just going to be this. P is equal to P0 plus gamma H on this line. And so in the case where, well, we said first when we looked at Bernoulli's equation that we could certainly look at, I'll come back to this in a second, but we could certainly look at drawing behavior between two different points for the streamline behavior. And if we do that, we get the Manometer Equation, which is exactly what we have here. But it also turns out that if we use this normal to the streamline equation, we also basically get the Manometer Equation as well, that we allow us to be able to define the pressure in the system. And so what's come out of this is really just the fact that we have this Manometer Equation. So that's the first part. So now, if we do the more complicated one, I'm going to get rid of these. So these are going to disappear, but they'll be, and I guess I can probably get rid of this as well. So we are now going to look at using this same equation on the top. But now we're going to look at these locations which are 3 and 4. So we know now that the curvature of this is not infinite. The curvature now is this. I suppose what we're going to do is that we have a radius here which we include. Let me get rid of the other changes that I made here just so it's not so crappy. So what we could do is we could say that we take this as a general radius for both points 3 and point 4. So clearly the radius of point 3 and point 4 are different from each other, but let's ignore that and let's take the average of the distance between them as this radius. And so now if we write this equation, we can do the same thing. We can write it as P3 plus density times this integral v squared over r dn plus unit weight z3. So we're just going to write it between these 2 points, just as before, is equal to P4 plus density, same integral, v squared over r dn plus unit weight times z4. Are we still on the screen? Yeah, we are. So we said that we've done a couple of things, a couple of simplifying things. One is that we've taken r to be the same in both places. They're not the same radius, but let's take it to being the same. And the second is that these are the velocities. I guess I didn't number them, but this is velocity at point 3, and this is velocity at point 4. And they're on an arc, but let's assume that they're equal to the same velocity as well. They're not quite equal to the same velocity, because this one, the whole idea of fluid over an aerofoil, the top fluid and the bottom fluid, they have to start at the front of the airfoil, the leading edge, and they have to join at the end. And so if the top distance is longer than the bottom distance, then the top one has to be traveling faster slightly. But let's ignore that here and take them as the same magnitude. And so what we're going to do is we are going to try and figure out exactly what is this pressure, right? We know this pressure. We know this pressure has to be atmospheric because it's sitting on the surface. And so we'd like to be able to figure out exactly what pressure at point 3 is. So what we could do is we could rewrite this expression as P3 is equal to, this is 0 because it's atmospheric. And so it's going to be equal to the unit weight times Z4 minus Z3. Okay. I'm just moving this term over here. So that gets rid of this and this. And it's equal to density, plus this term here, which is density multiplied by this V4 squared term over R dn minus density integral V3 squared term. And so if you think about what this term is, it's really an integration between R equals 0 and R equals, for want of a better term, R3 and R4, right? These radii. So this radius from here to here would be R4, for instance. And so if you think about what this integral is, the easiest way to think of that integral is that if you have a function, is that on the board? No? Is that on the board? So if you have a function that looks like this, and looks like some random thing, then if you integrate from 0 to R4, for instance, dr, it's actually n that we're using, then that integral is just this area that's included in here, right? That's all an integral is. So if you integrate from 0 to R3 dr, and this is R3, then that integral is just this area. So if you're subtracting an integral from 0 to R4 and an integral from 0 to R3, which are these two, then the difference between these ends up just being this difference in this component here. So that's physically what it is. So I'm getting very messy here, but the bottom line is that the integral from 0 to R4 dr minus the integral from 0 to R3 dr is just the same as the integral between these two limits. Right? Physically, that's all that is. And so that's a graphical explanation. So this expression here now becomes, if we write it out, P3 is equal to the unit weight multiplied by the difference in the elevations plus the density times the integral between R3 and R4 of this term V4 squared over R dn. And so, yeah, if we look down here, do exactly that. Yeah, right, okay. So now we can calculate the pressure at this point here as a function of P4, which is 0. And so if I clear this off a little bit and try drawing in here. Then physically what's going on is that if we look at the pressure with depth as we go down here, we know that the normal pressure distribution with depth would be equal to, let me draw it out to the side, P3 is equal to P4 plus unit weight times Z4 minus Z3. This is just H, right? This term here. So in other words, it'd be this linear term here. And we have that, this term here. And so what we have in addition to that is another term. The velocity will be some number. The velocity is always positive, right? It's along the streamline. So this has to be positive. The radius is positive. The density is positive. It's integrated just a constant between this length of these 2 points. So you can take that as being a positive. But the other thing is that if you look at the coordinate directions we have, this direction Z is positive upwards, but the normal to the direction of circulation, if you like, is pointing into the center here. This is our direction dn. You can see it right here, dn. So in other words, dn is equal to minus dz. And so if we substitute this integration here for the z direction, then this becomes a positive. Sorry. This becomes a negative. So this term here, if we substitute for dn, the term would actually be P3 is equal to unit weight, the difference in elevations. If we substitute this, and this term will be minus density, this integral between these two limits, R4 V over R dz. So all I've done is I've changed this for this. And the only important thing is that this integration now would just be between these two locations. If this is a constant, then this whole integral would just be this constant multiplied by the length difference between these, which is some number. And the only important thing to realize is that there's a negative sign here. And so physically what this would look like is that if you wanted to figure out exactly what the pressure distribution was here, is it has to be less than the hydrostat. It has to be less than the hydrostat because this is positive along a streamline, this is positive, and the integration gives you, as a result of that, a negative number that would just subtract an amount off here. If it was going through a curve on the opposite side, it would end up that the direction pointing into the center of the circle, I can't redraw it very well. I suppose if you could imagine that you have a flow along this direction and it goes. So if you have flow that does this, then in that particular case, the radius of curvature would look like this. The direction of the normal would be in this direction, and the direction of z is in the same direction. So this term is the opposite of this, and this sign convention would change. So this would be a plus instead of a minus. So in this particular case, if you're going into a dip, you can imagine being pushed into the seat in your car, and the pressure distribution, instead of being the red hydrostat here, would actually be an increase. So in this particular case, if you're holding a beaker, the pressure at the bottom of the beaker would be greater than the hydrostat as you go down. And if you go over a bump, because of this sign convention, it works out that it would be the green line in this particular case. Right? So that's behavior along a streamline. So really, I guess all we've done is we've validated the fact that we can define two equations. If we go back to where we started off today, just so we kind of reorient ourselves. We know exactly that Bernoulli's equation looks like this. And if we want to write it out in longhand, we can write it out as P over gamma plus elevation plus V squared over 2G is equal to constant. And that's one of our standard results. And all we've really added today is a second standard result, which is written down here, which is this bottom one here, which is that we have a very similar equation as I say, I always prefer to write it divided through by unit weight, just because it's easier. And that is that we have the same terms. We have a pressure term in both cases. We have an elevation term in both cases, which are identical. But the inertial term, F equals ma, the ma term that represents the acceleration in the system, is different. In one case, it's for linear acceleration along the streamline. In the other case, it's for, again, linear acceleration along a streamline, but it relates to the acceleration that occurs along a curved surface of some radius r. And just by some manipulation with the different directions, if it's on an external surface that's going over a hump, then you end up being less than gravity. So this ends up being a negative sign. And if you're going into a hump, then you're adding to gravity, and this becomes a plus, stays a plus sign. And so that's it. That's it, I think. So so that's it. So we could go through some examples, but I don't think we have time to do that. Okay.